Swayam Prabha. Digital India. Educated India.
Welcome to lecture 4 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is Simple Linear Regression Model. Actually, any econometric study begins with some propositions or some hypothesis regarding some aspect of the economy. You have some economic variables and basically your economic theory tells you that these economic variables are related with each other in some manner. So, you try to establish some kind of econometric model for those economic variables. Now, once you develop some economic relationship, some econometric model for those variables, your next objective is to estimate the parameters of the model, and after estimating the parameters of the model, you want to validate the model, whether your model works well or not, or whether your model is worthwhile to explain the proposed economic theory or not. So, you want to validate the model for this purpose. Now, the regression analysis provides a strong tool for econometricians. Actually, the objective of regression analysis is also to establish the relationship between different variables. So, one can use the regression analysis for fitting different econometric models, for validating different econometric models. Different tools of the regression analysis can be used for all these purposes. So, in this lecture, I am going to consider a very simple linear regression model, which involves a linear relationship between two variables. We try to explain the variations in one variable on the basis of variations in the other variable. Then we will consider the estimation procedure for estimating the parameters of this model. Actually, we will use the method of least square for estimating the parameters of the model. And then we will also consider some measures of goodness of fit of the model. So, now suppose you have two random variables x and y, and we are interested in getting answers to questions such as how y varies for changes in x, or explain the changes in y in terms of changes in x. So, we presume that y is affected by the changes in x, and this is our objective, to observe how y is going to change with x, and then we have to explain the changes in x in terms of changes in y. So, for example, how much the yield of wheat per acre, say we denote it by y, is expected to increase or decrease for the unit change in amount of fertilizer used, say x. So, x denotes the amount of fertilizer used and y denotes the yield of wheat per acre. And to get answer to this question, we require a relationship between y and x. The second example, how the circulatory strain reacts or blood pressure response, and we denote it by y, to different doses of a medicine, say x. So, x denotes different doses of a medicine and y denotes the blood pressure, and we are interested in explaining the changes in blood pressure or response of blood pressure for different doses of the medicine, that is x. Then this polymer modified cement mortar PCM is a new building material, and our question is how different polymer cement ratio x, we denote it by x, influence the PCM's compressive strength, and we denote this compressive strength by y. Again, to get answer to this question, we have to establish the relationship between y and x, and once we establish a proper relationship between y and x, then probably we can answer this question. So, basically we are interested in what is the functional relationship between x and y, how much confident we are about this functional relationship between x and y. We also want to answer this kind of question, how good this functional relationship is. Now, we consider a simple linear regression model or two variable regression model. So, we assume that there is a linear relationship between y and x. So, we write y equal to beta 1 plus beta 2 x. Then we also add a random error term u. These beta 1 and beta 2 are the unknown regression parameters, and of course, we have to estimate these unknown regression parameters, and for that purpose we go for some empirical study. We take some observations on x and y, and then we apply certain procedure for estimating beta 1 and beta 2 on the basis of observed data. Then this equation 1 is a regression line of y on x, and this relationship actually explains y in terms of x. And this relationship also tells you that y depends on x. As x changes, y also changes. So, y depends on x. So, we assume that y is generated through the model or system 1, and x is generated from outside the model or from outside the system. So, we are getting x from outside the system, and y is generated through this system, through this model. Then giving input x, if you give the input x, then the model gives the output y. So, for given x, given input x, we get the output which is denoted by y, and this output we get through the model. Then your objective is to predict y on the basis of x. In experimental sciences, if value of x is in control of the experimenter, then y is the response. In this example, the model or system 1, and x is generated from outside the model or from outside the system. So, we are getting x from outside the system, and y is generated through this system, through this model. Then giving input x, if you give the input x, then the model gives the output y. So, for given x, given input x, we get the output which is denoted by y, and this output we get through the model. Then your objective is to predict y on the basis of x. In experimental sciences, if value of x is in control of the experimenter, then y is the response. Say in this example, different doses of a medicine are in control of the experimenter. So, y is the response of blood pressure for different doses of the medicine. So, accordingly different terms used for x and y are as follows. Say if x is your independent variable, then y is your dependent variable, or x is your predictor, then y is the predicted variable. We are predicting y using the predictor variable x, then x is explanatory variable, then y is the variable to be explained by the model. We are explaining the variations in y on the basis of x. So, y is the variable to be explained and x is the explanatory variable. Then y is your recurrent and x is your regressor, or y is your response variable and x is your control variable. So, we use these terms for the variables x and y. Then u is called the random error or disturbance term, and this u is unobservable, and this u represents the factors other than x affecting y. Obviously, none of your model is perfect, but still you have to use your model for predicting y. You can't get a perfect model, but still. So, apart from x, there might be many other factors which are affecting y, and all those factors are taken care of by this term u. So, u is unobservable and it represents the factors other than x affecting y. We assume that expectation of u is 0. Sometimes your error may be positive, sometimes your error may be negative, but its expected value is 0. Variance of u is sigma square u. We also assume that u and x are uncorrelated, so that expectation of x u is 0. Since we are assuming that x is generated from outside the model and u is the part of the model. So, we can assume that u and x are uncorrelated, or you can say expected value of u given x is equal to expected value of u, and this is 0. Then if you take expectation of y given x, then expectation of y given x is equal to beta 1 plus beta 2 x, because expectation of u becomes 0. And remember that u is the random error term. So, u introduces the randomness to the model. Your regression equation is y equal to beta 1 plus beta 2 x plus u. Then beta 1 plus beta 2 x, this is the non-random part, you can say, and u makes your model a stochastic one. This equation 2 gives the population regression function, and it is a linear function of x. Whenever we say it is a linear function, it means it is linear in regression parameters beta 1 and beta 2. So, beta 1 plus beta 2 x gives the systematic part of y, that is part of y which is explained by x, and u is the part of y which remains unexplained by x. And then you can easily verify that u is equal to y minus expectation of y given x. So, this is the difference between the observed and expected realizations of y. The observed y minus expected value of y given x gives you u. Here beta 1 is the intercept term, and for x equal to 0, the expected value of y is beta 1. Or if you consider the straight line, say y equal to beta 1 plus beta 2 x, then this straight line cuts the y axis at point beta 1. Beta 2 is the slope coefficient. If you differentiate expected value of y with respect to x, then you obtain beta 2, or you can say beta 2 is the expected change in y for a unit change in x. Now, your next objective is to estimate the regression coefficients beta 1 and beta 2, and for that purpose we use the method of least squares. So, for estimation purpose we require some observed data. So, we take bivariate observations on two variables x and y. You have n pairs of observations x 1 y 1, x 2 y 2, so on x n y n. So, and then your objective is to determine the relationship between dependent and independent variables describing the phenomena or the process in the best possible way. So, we write corresponding to the jth observation, we write y j equal to beta 1 plus beta 2 x j plus u j, j equal to 1 to n, and then you have to estimate beta 1 and beta 2. Again u j is the error term having mean 0 and variance sigma square u. Then method of least squares estimate beta 1 and beta 2 by minimizing the error sum of squares. So, suppose we have some observations on x and y, and then we have plotted those observations. So, these are different observations, and this straight line is the best fitted straight line. Then we minimize to find the values of beta 1 and beta 2, or to obtain this best fitted straight line, we minimize the error sum of squares. So, we take the error y j minus beta 1 minus beta 2 x j, and you observe that y j minus beta 1 minus beta 2 x j is actually the distance between this observed value and the straight line parallel to the y axis. And why we are interested in the distances parallel to the y axis? Remember that your main focus or your main objective is to predict the value of y. So, that is why you want to minimize the distances between observed and predicted or expected values of y. So, you are mainly interested in these distances. Now, sometimes these distances are positive and sometimes these are negative. So, to make it free of sign, we take a square of this, and then we take summation over j, summation over all the observations j equal to 1 to n. So, we minimize S, and we denote the resulting estimators, which are called the least squares estimators, by beta 1 head and beta 2 head. Again, to obtain beta 1 head and beta 2 head, you have to minimize S, or for that purpose we differentiate S with respect to beta 1, and then we write beta 1 equal to beta 1 head, beta 2 equal to beta 2 head. And when we differentiate S with respect to beta 1 head, we obtain minus 2 times summation over j y j minus beta 1 head minus beta 2 head x j, we put it equal to 0. And this finally gives you the relation summation j y j equal to n times beta 1 head plus beta 2 hat summation x j. Again, when we differentiate s with respect to beta 2 and we write beta 1 equal to beta 1 hat, beta 2 equal to beta 2 hat, then we obtain this relation, which can be simplified as summation j x j y j equal to beta 1 hat summation j x j plus beta 2 hat summation x j square. So, you get these two equations and then we solve these two equations for obtaining the values of beta 1 hat and beta 2 hat. So, from the first equation we write y bar equal to 1 by n summation y j, which is the mean of all the y j's, and x bar equal to 1 upon n summation x j. So, from the first equation we obtain beta 1 hat equal to y bar minus beta 2 hat x bar, and then we write it equal to say b 1. Again solving those two equations, you obtain beta 2 hat equal to summation x j y j minus n times x bar y bar divided by summation x j square minus n times x bar square, and we write it equal to b 2. Or alternatively, b 2 is equal to this numerator is actually equal to summation j x j minus x bar y j minus y bar, and denominator is equal to summation j x j minus x bar square. And if we divide both the numerator and denominator by n, then this numerator gives you the covariance between x and y, denominator gives you the variance of x. And you know that the covariance between x and y is equal to, this is equal to the correlation coefficient between x and y into S x into S y, where S x is the standard deviation of x, S y is the standard deviation of y. So, and this denominator is equal to S square x. So, finally, you obtain B 2 is equal to R S y upon S x. R is the correlation coefficient between x and y, and S square x is the variance of x, S square y is the variance of y. Then the predicted value of y, say y j hat is equal to b 1 plus b 2 x j, corresponding to x j you get this predicted value of y. Or we substitute the value of b 1 from here, this value of b 1 we substitute here. So, you obtain y j hat is equal to y bar plus b 2 x j minus x bar. Then your prediction error E j is y j minus y j hat, or you can write y j equal to, this part actually gives you y j hat plus E j. Then from the normal equations which we have derived here from these two equations, you observe that summation E j is equal to summation y j minus n times b 1 minus b 2 summation x j, which is equal to 0 from the first normal equation, and summation x j E j is also equal to 0. So, this prediction error has mean 0 and it is uncorrelated with x j's. Then E j's have mean 0 and these are uncorrelated with x j's. Now, to investigate the finite sample properties of these least square estimators b 1 and b 2, let us write C j equal to x j minus x bar divided by summation over j x j minus x bar square. Then obviously, summation C j is equal to 0, because summation C j involves summation x j minus x bar, which is equal to 0. sum of deviations from mean of xj is 0, and summation Cj square is equal to summation xj minus x bar square divided by square of summation xj minus x bar square. So, finally, you obtain 1 upon summation xj minus x bar square, and if you take summation Cj xj, then summation Cj xj is equal to 1, because summation Cj xj involves and then this is equal to summation xj minus x bar square, and in the denominator also you have summation xj minus x bar square. So, finally, you obtain this is equal to 1. So, summation Cj xj is equal to 1. Now, you can write B 2 equal to summation over j Cj yj minus y bar. Then this is equal to summation Cj yj, and the second term is y bar summation Cj, and summation Cj is equal to 0. This we have already shown. So, expected value of B 2 is equal to summation over j Cj expected value of yj, and expected value of yj is equal to beta 1 plus beta 2 xj. So, actually you obtain summation j Cj beta 1, you can take beta 1 outside, and so you get 0 here, and then beta 2 summation Cj xj, and summation Cj xj is equal to 1. So, finally, you obtain expected value of B 2 is equal to beta 2. So, B 2 is an unbiased estimator of beta 2, and expected value of B 1 is equal to expectation of y bar minus expectation of B 2 into x bar. Expected value of y bar is beta 1 plus beta 2 x bar. Actually, expected value of yj is equal to beta 1 plus beta 2 xj. So, expectation of y bar is equal to beta 1 plus beta 2 x bar, and then you have expected value of B 2 equal to beta 2. So, you get beta 2 x bar. So, finally, you obtain beta 1. So, expected value of B 1 is beta 1. So, B 1 and B 2 are unbiased estimators of beta 1 and beta 2 respectively. Further, you can obtain the variances of B 1 and B 2 also. Variance of B 2 is equal to sigma square u summation over j C j square. Actually, the expression for B 2 is summation over j C j y j, and variance of y j is sigma square u. Actually, variance of y j is same as the variance of u j. So, variance of B 2 is summation over j C j square, variance of y j which is sigma square u, and then summation C j square is equal to 1 upon summation x j minus x bar square. So, finally, you obtain this expression, and variance of B 1 is equal to variance of y bar minus B 2 x bar. So, this is equal to expectation of y bar minus, you take expectation of y bar here. So, beta 1 minus beta 2 x bar minus B 2 x bar minus beta 2 x bar, and then we take whole square. Then y bar minus beta 1 minus beta 2 x bar can be written as say u bar. U bar is equal to 1 upon n summation u j minus, you get B2 minus beta 2 x bar whole square. Then you get expectation of u bar square or variance of u bar. Since each uj has variance sigma square u, so variance of u bar is sigma square u by n plus variance of B2 into x bar square. Variance of B2 we have already obtained. So, we substitute the value of variance of B2 here into x bar square, and cross product term has expectation 0. So, you obtain this expression for the variance of B1. Further, the summation xj minus x bar square is equal to summation xj square minus n times x bar square. So, you can simplify the variance of B1 as say sigma square u you get, and in the denominator you obtain n times summation xj minus x bar square. In the numerator you get summation xj minus x bar square plus n times x bar square. So, finally, you get summation xj square. So, this is the final expression for variance of B1. Now, we obtain an unbiased estimator of sigma square u. Actually, we have summation Ej square equal to summation Yj minus Yj hat square, and then we substitute the value of Yj hat, which is equal to y bar plus B2 xj minus x bar, and then we take these two terms together and then we take square of this. So, summation you get summation over j Yj minus y bar square plus B2 square summation xj minus x bar square minus 2 times B2 summation xj minus x bar Yj minus y bar. And then you get the first term here. Actually, this last term is B2 and summation xj minus x bar Yj minus y bar is equal to B2 times summation xj minus x bar square. This part is equal to B2 times summation xj minus x bar square. So, you get minus 2 times B2 square summation xj minus x bar square. So, finally, you get this expression. Then Yj minus y bar is equal to beta 2 xj minus x bar plus uj minus u bar. So, from here we obtain expectation of summation Ej square equal to expectation of summation uj minus u bar square plus beta 2 square summation xj minus x bar square minus we take the expectation of this term, expectation of B2 square is actually equal to variance of B2 plus beta 2 square. So, you get beta 2 square here plus this is the expression for variance of B2 into summation xj minus x bar square. And then you can easily simplify it. You take expectation of this term, which is equal to n minus 1 times sigma square u plus beta 2 square. You get this term, and but this term cancels out because here you get minus beta 2 square summation xj minus x bar square. So, you get minus sigma square u, and again this term cancels out. So, finally, you obtain n minus 2 times sigma square u. Therefore, an unbiased estimator of sigma square u is sigma hat square u equal to summation E j square upon n minus 2. So, you can easily obtain an unbiased estimator of sigma square u also. Now, sometimes we write the model as deviation from mean. So, y bar is actually equal to b 1 plus b 2 x bar, because summation E j is equal to 0. So, you can write y bar equal to b 1 plus b 2 x bar. So, y j minus y bar is equal to b 2 x j minus x bar plus E j. Then we multiply this equation by x j minus x bar. We multiply both sides by x j minus x bar, and then we take summation over j. And you also observe that summation j x j minus x bar E j is equal to 0. So, if we multiply this last term with x j minus x bar, take summation, then we get 0. So, finally, you obtain summation j x j minus x bar y j minus y bar equal to b 2 summation x j minus x bar square. From here, you obtain the value of b 2 as summation x j minus x bar y j minus y bar divided by summation x j minus x bar square. Then we also observe that summation y j hat minus y bar E j is equal to b 2 summation x j minus x bar E j, which is equal to 0. So, this E j is uncorrelated with the predicted value of y j hat. Then the total sum of squares or the total variation in y is summation over j y j minus y bar square. And this part summation y j hat minus y bar is actually the sum of squares explained by the regression, because this is the predicted value of y, or this is the part which we have explained by using the regression of y on x, and this is actually equal to, we have already shown that this is equal to b 2 square summation x j minus x bar square. So, you get total sum of squares explained by the regression here. Then unexplained or residual sum of squares is summation E j square. So, this is the residual sum of squares. Further, you can write this total sum of squares as summation y j minus y bar square equal to summation over j y j hat minus y bar plus y j minus y j hat square. So, we have subtracted and added y j hat, and then we take square. So, you get summation over j y j hat minus y bar square plus this is actually equal to E j. So, you get summation E j square, then you also get the cross product term, which we have already shown that the sum of cross product terms, that is summation y j hat minus y bar y j minus y j hat is equal to 0, or you can say summation y j hat minus y bar E j is equal to 0. So, this total sum of square is equal to the explained sum of square or the sum of squares explained by the regression plus unexplained or residual sum of squares. Total sum of squares is equal to explained sum of square plus residual sum of squares. Now, the degrees of freedoms of total sum of squares is n minus 1, because remember the expression for total sum of square is summation j equal to 1 to n y j minus y bar square. It has n terms, but it has one constraint also, summation over j y j minus y bar is equal to 0. So, the degree of freedom of this total sum of square is n minus 1. Then the degrees of freedom of explained sum of square is 1. and the residual sum square has degree of freedom n minus 2, because you are taking summation from j equal to 1 to n e j square, but it has two constraints also, two linear restrictions. First is summation e j is equal to 0, second is summation e j x j is equal to 0. So, degree of freedom reduces by 2 and you get n minus 2 here. So, n minus 1 is equal to 1 plus n minus 2. Degrees of freedoms are also additive, just like the sum of squares. So, this is how we get the analysis of variance for your model, the simple linear regression model. You have explained sum of square ESS, then you have residual sum of square, and if you add these two, you get the total sum of square, and corresponding degrees of freedoms are 1, n minus 2 and n minus 1. So, we have decomposed the total sum of square into the explained and residual sum of squares, and similarly we have decomposed the total degrees of freedoms into the degrees of freedoms of explained sum of square and degree of freedom of residual sum of square. Now, if you take summation j equal to 1 to n y j hat minus y bar square. So, this is equal to b 2 square summation j equal to 1 to n x j minus x bar square. Then b 2 is equal to r s y upon s x. So, b 2 square is equal to r square s square y upon s square x, and then you have summation x j minus x bar square, which is equal to n times s square x. So, you get n times s square x here, s square x will cancel out, and n times s square y is equal to summation over j y j minus y bar square. So, summation j y j hat minus y bar square is equal to r square summation over j y j minus y bar square. Or you can write r square equal to summation j equal to 1 to n y j hat minus y bar square divided by summation j y j minus y bar square. Now, remember that this numerator is the total variation which is explained by the model. So, this is the variation and this denominator gives you the total variation. So, basically this r square gives you out of total variation proportion of variation explained by the model. R is the correlation coefficient between x and y. So, r square is the square of correlation coefficient between x and y, and r square gives you the proportion of variation explained by the model out of the total variation. You may consider r square as a measure of goodness of fit of the model. When we say that our regression is good, when we are able to explain the maximum possible variation out of total variation, we are able to explain the maximum possible variation. So, r square should be as close to 1 as possible. means obviously the range of R is from -1 to +1. So, range of R square is from 0 to 1. R square equal to 0 means the correlation coefficient between x and y is 0. So, this is one explanation of correlation coefficient. Another explanation in regression is if R is equal to 0 or R square is equal to 0, your regression is not able to explain any variation in y. So, it is not worth using the regression. In correlation, if the correlation coefficient is equal to +1 or -1, then we say that x and y are perfectly correlated. And if R is equal to +-1, then obviously R square is equal to 1. And R square equal to 1 means in terms of regression, it has the explanation that if R square is equal to 1 or if it is close to 1, then your regression is good in the sense that you are able to explain most of the total variation present in yj on the basis of your regression. And since you are able to explain most of the variation in y on the basis of x, your x is a good predictor for y, or your regression line provides a good predicted value of y. So, it is a good regression. So, you may consider R square as a measure of goodness of the model. So, in this lecture we have considered a simple regression equation for two variables. If you have one variable x which affects another variable y and you want to explain the variations in y on the basis of variations in x, and if you believe that the relationship between y and x can be represented by a straight line, then you can use the simple regression between y and x. We have also discussed the method of least squares for estimating the parameters of the model, for estimating the regression coefficients as well as the error variance. We have shown that these estimators are unbiased. Further, we have considered the analysis of variance of the model, means you can decompose the total variation present in y in terms of the variation explained by the model plus the residual variance or total variation in residuals. Then we observed that R square provides you a measure of goodness of fit of the model, that is R square is actually the square of the correlation coefficient between x and y. Of course, in many practical applications, instead of one variable you may have a set of more than one variables which you would like to explain the variations in y, means y depends upon more than one variables, variations in y depend upon more than one variables, and in that case we use multiple regression. In the next lecture we will consider the multiple regression and method of least squares for the multiple regression. Thank you.
Hi, I'm Chitwan Lalji, a PhD student of Health Economics under the supervision of Dr. Debayan Pakrashi from the Department of Humanities and Social Sciences, IIT Kanpur. In one of my essays, I'm interested in understanding the relationship between consumption of fruits and vegetables and various health indicators. Health indicators, both subjective and objective health indicators like mental health, self-assessed health, various measures of blood pressure and various measures of cholesterol. Measures of blood pressure like systolic and diastolic BP, you have your incidence of high BP, MAP and incidence of high MAP. And as far as cholesterol is concerned, I have tried to concentrate more on total cholesterol, good cholesterol and incidence of high cholesterol. Now before I go on to what have been my major contributions and various policy implications, I would like to briefly tell you about the policy initiatives of WHO and various countries. The WHO, that is the World Health Organization, it started with a campaign of 5 a day. That is, you should have 5 portions of fruits and vegetables per day. That would be approximately, you could say, 400 grams of fruits and vegetables. Now, a portion, before we go further, I'll just tell you what exactly is a portion. One portion is equivalent to a medium-sized apple, or one small glass of fruit juice, which is approximately 150 milliliters, and maybe 3 teaspoons of vegetables. So, the WHO went with a 5 a day campaign, which was further taken up by various countries. Countries like UK, Netherlands, Germany, Norway, they adopted the 5 a day policy, while some went for expansionary dietary policies like France, Australia, Canada, Denmark. So, for example, Australia, it went for 2+5 policy, in which it said that you should consume 2 portions of fruits and 5 portions of vegetables per day. And USA went for a policy of fruits and vegetables more matters. That is, you must consume more and more fruits and vegetables. Now, irrespective of these expansionary dietary policies and dietary propagations, it has been found that only 28% of women and 25% of men, they actually meet the recommended dietary norms of 5 a day portion. So, the major contribution of my work is firstly to find an association between fruits and vegetables, whether there exists a relationship between fruits and vegetables and health indicators, and if they exist, whether due to heterogeneity in the data. So, I will be doing it according to age, by gender and by your weight. So, apart from that, I will go for policy recommendations, in which I am basically studying how much fruits and vegetables matter. Apart from that, which type matters more. So, for that I have taken data from the Health Survey of England. Health Survey of England is an annual survey which takes data, which conducts information regularly on demographic and socioeconomic characteristics. You have your lifestyle behaviors like an individual smokes or doesn't smoke, alcohol consumption, you have your sedentary and physical activities, and you have various health indicators also which have been collected. Before I go on to what exactly is my research, I would like to concentrate more on fruits and vegetables, like what kind of questions were asked in the survey. Questions like, what kind of fresh fruit do you eat? Did you eat any dried fruit yesterday? Don't count dried fruits in cereals, cakes. Apart from that, for vegetables, they asked how many tablespoons of vegetables did you eat yesterday? So, approximately after this whole survey was conducted, data was converted into portions of fruits, and like for example, 3 tablespoons of vegetables is equivalent to 1 portion. So, data was converted and provided to the users, that is us, from the UK Data Health Survey. So, the major contributions of my paper is that I found a strong negative association between intake of fruits and self-assessed health, then various measures of blood pressure like mean arterial pressure, high blood pressure, systolic and diastolic BP, and your total cholesterol. Apart from that, I have found a strong positive association between consumption of vegetables and good cholesterol. So, it is recommended in a way that if you want to control your blood pressure, you must consume more and more fruits. And as far as vegetables are concerned, they impact your good cholesterol. Apart from that, I went in for a falsification test. A falsification test is basically conducted to know whether the model that you have adopted and the conclusions that you are drawing are not spurious. So, if a falsification test is done to know, in a way it is tested by seeing an indicator, a health indicator which is not being impacted by your consumption of fruits and vegetables, and then we see whether there is significant result or not. If there is no significant result, that means your model is good and your results are non-spurious. So what we did is, for falsification test, we took ear complaints and infectious diseases. Now ear complaints, like if you are deaf since birth or you have some kind of imbalance, body imbalance, that is not being impacted by your consumption of fruits and vegetables, and we did find insignificant results. Apart from that, infectious diseases like HIV, AIDS, etc., we found similar insignificant results, indicating that our results are non-spurious. Apart from that, we went, since there was a lot of heterogeneity in the data, like by gender, by age and by weight, we did the regression analysis. We found results which stated that as far as fruits are concerned, it impacts a male's health more than a female's health. So it is basically said a man should consume more fruits to impact his health, whereas as far as vegetables are concerned, they impact a women's health more. But this has been only seen as far as cholesterol is concerned, the various measures of cholesterol like total cholesterol, good cholesterol and your incidence of getting high cholesterol. Now after this, we went in for a policy implication, and in the policy implication we tried to find two policy implications: what matters and exactly how much portion matters. So as far as how much portion matters, we have found that on an average 5 or more portions of fruits impact your overall health, that is your self-assessed health, your MAP, your incidence of high MAP and incidence of high BP. But if you want to have a good mental health, so you can optimize your mental health by consuming 3 or 4 portions of fruits as well. And similarly, as far as self-assessed health and total cholesterol is concerned, an individual must consume 4 to 5 portions to optimally have the impact of consumption of fruits. Apart from that, vegetables have had a very little impact on your health. It only impacts your incidence of getting high MAP and high BP, and it's seen that only it impacts when you consume 5 or more portions of fruits. So an optimum consumption of 5 or more portions of fruits and vegetables are recommended, but fruits have a more impact on your overall health, on various measures like self-assessed health, mental health, your various measures of blood pressure and various cholesterol levels. Another thing that we find is which type of fruit matters. It has been seen that all size fruits, they impact your self-assessed health, your systolic and diastolic blood pressure, your mean arterial pressure, your high BP and incidence of getting high MAP and high cholesterol. But we find that as far as frozen fruits or canned fruits are concerned, they help in regulating your incidence of getting high MAP or high BP, but it has a trade-off. That means there is something negative happening. It reduces the good cholesterol in your body. Apart from this, if you have an incidence of getting high cholesterol, it is recommended that you must consume fruit juices because it has an impact in reducing your probability of getting high cholesterol. And dried fruits, they impact your self-assessed health. As far as vegetables are concerned, very little impact has been seen. It has only been seen in case of portion of salads and its association with self-assessed health. Another thing that they have seen is vegetables in composite, they have an association with good cholesterol. So overall, my research basically says that there is an association between consumption of fruits and vegetables and various health indicators, and it is highly recommended that an individual, in order to be healthy, must consume 5 or more portions of fruits and 5 or more portions of vegetables per day, but fruits have a more impact on your overall health. Apart from that, all size fruits, they have a better impact on your overall health, your mental health, various measures of blood pressure and cholesterol. So, thank you.